In this video, I'm going to go through task 4 of the ISP for further mechanics and EM fields, which is mainly about the idea of capacitors. Now, capacitors can be paired with the resistors to affect voltage and to describe the charging and discharging of capacitors qualitatively, quantitatively, and graphically. Okay, so let's get straight into explaining everything, which is very straightforward this time round. So the first thing is explain how you can calculate the charge stored in the capacitor, its potential difference, and its energy stored, in the capacitor using an equation and by using voltage against charge graph. Okay, I should say graph at the end of it rather than Q charge. That wouldn't make sense. We want the graph. We want to figure out how to do it. Okay, so if I bring up a slide, if I enable the content, and let's get that full screen. So we'll see if we have a voltage against, if we move away a charge graph, okay, the area under this graph, okay, the area under allows us to see the amount of energy stored in the capacitor. So it's half base times height, so that's going to be half QV, but Q is also equal to CV, so therefore the energy stored in the capacitor is half CV squared, or half Q squared over C. Note that the energy used by the cell to charge the capacitor is equal to just the charge times voltage. So only half of it actually goes into the capacitor. Okay. So the other half of the energy is lost in the circuit as heat energy as the capacitor is charged, I should say, not changed. As capacitors are able to store energy, they can be used as backup systems essentially for electrical devices like computers and mobile phones. Okay, so that's the idea of a capacitor and what it can actually do. Okay, so let's quit out that slide and get back onto the ISP. So that's the main information you need to cover into there. So remember to pause the video back on that slide if you need to copy the information across. Describe the discharging, charging of the capacitor and explain the importance of the time constant. Okay, so remember the idea that it's exponential decay if it's discharging or exponential growth if it's charging. And remember the time constant is equal to the resistance times by the capacitance. Okay, and at the time constant it will be at 37% of the original value. Okay, that's the idea. So 63% of it would have gone, while 37% of the original value is where it's now at. Okay, so again we've got some nice stuff in the PowerPoint on here. I'll just get to the right slide. So we've got the slide here on charging capacitors. So we've got a current time graph, but equally that could be voltage or it's a voltage time graph, okay, but this is what it would look like if it was charging. Potential difference and current would look like, the potential difference of charge would look like this, okay. Got a slide over here that again goes through the idea of what's happening when it's charging. If I just pull that out of the way for now, you could have a read of that if you need to. Remember it's discharging, you have the idea of decay. Data shown there with charge and voltage. So remember time constant is a similar idea to that of half-life, but it's not how long it takes to get down to half. It's 0.37 of the original value. So remember the rate of removal of charge is proportional to the amount of charge remaining. That's the idea of it being exponential. Let's again expand on this. So that value of 37 comes from 1 over E, which is the exponential value on a calculator. Right, so remember the time constant is just resistance times capacitance. And there are your equations for it. So Q0 is initial charge, therefore V0 will be initial voltage and I0 will be initial current. So remember we can do this in terms of natural logs as well. So this goes through step by step how to do the natural log part of this. So we go through a lot of detail on this in class now, a lot of you do maths and further maths as well, and this is covered in there. So make sure you can do this. If you need extra help on this, please come to find me. But it's pretty straightforward once you get into the habit of it. Okay, so that's the explaining everything done. Let's now get stuck into the rest of the document. Bring the webcam back up. There we go. So into the questions now. So we've got a capacitor. There's energy stored in this capacitor that allows the energy source to act as an LED. Calculate the value of the capacitance of this capacitor. So we've got voltage and we've got a current. Okay. So from voltage and current we've got to get to capacitance. It's the idea they're asking for this question. So remember a couple of key things about this. you're going to look for units on either axes, okay? So voltage is straightforward in volts, and coulombs is straightforward in charge. Remember, quite often when it comes to charge, they use very small values of charge, and when they're so occasionally it's in millicoulombs. So right, the idea that we need to do over here is to take a value of current and voltage and divide the voltage. Divide the charge. A value of charge and voltage and divide the voltage by charge. Remember, Q is equal to CV. So C for capacitance is going to be equal to Q over V. Straightforward for that one. And remember, the unit of capacitance is farad. Use the graph to derive the expression W is equal to half QV. So remember, you got the idea of strips of Q, which was detailed in the PowerPoint slide and also in your book. And if you add up all the strips of changes in Q, if you add up all the strips of changes in Q, that's going to tell you strips of Q times by V. Changes in Q times by changes in V. If you made loads of strips of that up and you added them all together, that will tell you the area under. So essentially related to the idea of the area under the graph. So essentially you've got to show that on one axis what you're doing is multiplying voltage by charge. You're multiplying charge from one axis by voltage or potential difference on the other axis, and you have to half it because it's a triangle. So it's a pretty straightforward answer. Have a look at the mark scheme if you want a bit more detail on that, but it's a pretty straightforward question to get for 3 marks. Remember, the energy stored is the work done. Calculate the energy stored by the capacitor when it has 4 volts across it. Again, we're just looking at the area under the graph. Okay, up to 4 volts only. So don't go beyond this 4 volt line here. That's what they want, the area under here. Up to that 4 volts. Okay, so it's going to be 4 times by 5 divided by, or 4 times by, I think that's 4.8 divided by 2, or something along that, or something along those lines. Okay, so just be careful with your change in voltage and change in charge. Okay, again, I won't go through that in detail. It's something that you can figure out yourself. The energy shows the charge of a capacitor varying with time. Okay, so we've got the idea of a charge decaying over time. Explain why the output power from the LED decreases with time. Okay, well, if the charge decreases, that means the voltage decreases, therefore the current's going to decrease. Remember, voltage is energy per unit charge, so if the charge decreases, the voltage must decrease because it's going to be less charge. So what that actually means in the long run is P equals IV. So if V has gone down or I has gone down, then power must go down as well. So this links the, it says tying in essentially that equation there with P equals IV. Okay, because if this goes down, the capacitance is constant, because it's the same capacitor, then voltage goes down. If voltage goes down, then power must go down. So you need to really mention those two equations with the idea of things decreasing. Okay, so that's power equals current times by voltage. Nice question to get there for a couple of marks. A couple of people forget that. It's a synoptic element, time back to power from unit 2. Use the graph to determine the time constant for the LED circuit. Okay, so remember the time constant is the time it takes to get down to 0.37 of the original value. So you've got to figure out what the original value is, multiply that one 0.37, and then read across what the value of that actually is in terms of time. So the original value is about 3.4. My version of the graph isn't very good. Your printed out version will be better. I need to multiply about 0.37 to figure out what the value would be. So you're looking at about 1.25, 1.26. Okay, so we're looking about over here somewhere, about 125-ish. Okay, that's what we're ending up with. So I was drawn on the screen with my pen. You won't be able to see that. So there's my calculation. 3.4 times by 0.37 to find the value of time for time constant. So you end up with about 1.26. So that's going to be about over here somewhere. You draw a line across, you come down, it's about 1.2, 1.25, something along this. So 120, 125, somewhere along that sort of lines. Okay. It's a nice 10-mark question to get started there. Research suggests that big capacitors may soon be able to act alongside batteries as a way of storing significant amounts of energy. So they've used a capacitor of 2,500 farad. It's massive compared to what we're used to. We're used to microfarads, remember. Okay. So one of the parts of research considers a leakage charge through the insulating material between two capacitance plates. In one experiment, researchers charged the capacitor to a potential difference of 8 volts. calculate how much energy this capacitor stores when charged. Okay, so we're using our equations from before, so that's half CV squared, we've got C, we've got V over here, so remember energy stored in capacitor is equal to half CV squared. So you end up with a really large value of, just double checking I'm using the right equation actually, half CV squared. Pretty sure that's the right one, just going to double check. Just into the equation list, which is just up there. There we go. That's waves, that's unit 2. Still unit 2, unit 4, here we go. Capacitance half QV, and therefore if you replace Q with CV, it's going to be half CV squared. Yep. Always remember to check the equation you're using if you're a bit unsure. So half CV squared. So when you put that through, you should end up with a value of about 5,000. Okay. Next, the measured the percentage difference every 10 days. Remember it's in joules. So it's much larger than 5,000. I've just said that value off the top of my head. And just reading the mark scheme over it, they've written 5,000 in there as well. So there's just checking it's the right question. I'm actually looking at in the mark scheme as well. Yeah, it looks like it is. I think we've just made a small mistake there. Let's put it through ourselves. Half. Oh no, actually no, it is right. I'm just looking at the numbers wrong around. Because remember, 8 squared is going to be 64, we're going to get half that essentially. And then times that by, okay, no, they're saying 5,000. 5,000 doesn't look big enough. Have I missed a point here? Oh, it says 2 volts. There you go, there's the point I'm missing. We're not charging up to 8 volts, charging up to 2 volts. So yes, a silly mistake for me there, not reading the entire question. So 2 squared would be 4, half of that's going to be 2, 2 times by 2,500 is 5 joules. Yep, so make sure you don't just jump for the 8, because if it's at 8, 2 volts is what they used. Okay, so in this table over here, they're wanting the log of the potential difference. So essentially just natural log these values, so just do on your calculator, just to prove that, I won't do one of the ones you've got here because you can do those, but what I'll do is I'll show you how they've done this so that you know how to do it. It's literally straightforward, pressing natural log. So that's this button on your calculator here, okay, ln as some people say, and then into the brackets, writing the value you want a natural log of, so let's put 6.34. That shows you how they got their 1.84. Okay, so you should do the same for the other 3 underneath there, pretty straightforward. That's part B. Plot a graph on a piece of paper to show how PD is falling exponentially. Okay, so on that graph what they want is the log of y against x, so a log of y against t. So if you have the graph of natural log of y, v against t, I'm saying it completely wrong. So you should end up with a graph that will intercept the x-axis, so it will have a negative gradient like this, and then from that you can actually figure out certain values. Okay, so that's the graph they want. Okay, and if it's a log graph and it's got a straight line, it must be falling into that exponentially. Use a graph to find the value of the resistance of the insulating material between the capacitor. Okay, so from the explaining everything task, the gradient of this, okay, is minus 1 over RC. Okay, that's a fact you do need to know. So you need to use the gradient to allow you to figure out the value of the resistance. So you got the value of the capacitance from above, 2,500. 1 is just 1. Remember, this is a minus, so the value of the gradient is a minus value as well. So you put your value of the gradient in there. You rearrange for R essentially, so that's 1 over the gradient times by C is equal to your value of R minus. There you go. Straightforward. So remember, you have a minus gradient, so the minuses will cancel, and therefore you figure out the value of your resistor. That's D complete. Right, so we've got a diagram of capacitor and resistor connected to 6 volt battery. Both the ammeter and the battery have negligible internal resistance. Switch is closed. Sometimes later the ammeter reads 20 microamps. Show that the potential difference across the capacitor at this instant is 2 volts. So we have the voltage. Okay, we have the current. Sorry, they want the voltage. We have the current. Okay, so if we want the PD across the capacitor, okay, what we're going to need to do is use the idea of V is equal to IR. Okay, so we know the current through the resistor is the same as the current through the capacitor, okay, because it's a series circuit. So that allows us to figure out the potential difference across here. So we're using V equals IR essentially. Remember, this ties back to a lot of Unit 2 DC electricity stuff. So go back through the ISP tasks if you need to for that, if you feel electricity is not a strong point for you. So V equals IR. That's the idea we're using. Okay. Well, they want the voltage. Okay. With all the potential difference. Okay. They want to show that it's 2. So we want to multiply current by the resistance essentially. So the current is 20 microohms. So we're figuring out for the resistor first, then we're going to take this voltage away. So do follow me through. Don't think that I've got confused again here. I haven't. We're going to figure out the voltage across this one and take it away from the 6. So we're doing 20 microamps, so 20 times 10 to the minus 6. And we're going to times that by 200 kilo ohms. So we end up with 4 volts. So this over here has got 4 volts. If 6 volts comes in, so you do 6 minus 4, which means that must be 2. Calculate the charge stored in capacitor when the potential difference is 2 volts. Potential across it is 2 volts. So PD is 2 volts. Capacitor has a value of 560 microfarads. Okay, and they want the charge. So that's just from before the idea of Q is equal to C times by V. Very straightforward. Calculate the electrical energy now stored in capacitor. Again, straightforward. W is equal to half CV squared. Calculate the electrical energy transferred in the battery up to this instant. Okay, so this is where they're getting you to think a bit differently. Okay, this time you need to use the idea of W is equal to Q times RV. Let me get the calculator out of the way. Okay, the reason why is because they're talking about the battery now and not the capacitor. So that's how much electrical energy will be transferred in the first instance. Okay, so the idea that you've got there is you need to multiply the charge by the 6 volts. Okay, so the charge is actually going to have the charge that you've got from before up here, okay, times by the voltage of the battery, which is 6 volts. So you know there's going to be a difference between these, okay, because there's energy lost inside the circuit. What is the main reason for the energy difference between the values calculated in C and D? Okay, so remember, energy lost in thermal or heat energy. Okay, so the idea of work being done against resistance is essentially what's going on. Okay, that's the idea. Don't just state it in terms of energy dissipated or energy is lost to surroundings. Go through it in detail. It's the idea of thermal energy due to this work against resistance. That's the end of ISP task 4. We've got one left to do, task 5, which is all about magnetic fields and electromagnetic induction. Thank you for watching.